Oh, right. So the questions I gave you last week, I got a couple of what about the graphs. So the first worksheet I think was okay, drawing the graph. The only thing I can give you feedback on, let me find the actual paper. So this one, the drawing the graph, you're all pretty good. What I saw of that, I mean, I think this is pretty standard, just comparing the same. I think this is pretty like doable. The only thing I would suggest is, and these bits are okay, what can you say about the amount? So the amount was the same. Yeah, the amount was the same, it was just they ground one up and then the other one they didn't. What's the purpose? So the purpose is like their aim. What were they doing? They're trying to see what the rate of reaction, the rate of reaction, how the particle size affected it. The dependent and independent. So dependent is what you're measuring, and you're measuring the amount of time it took to lose that mass. I can't even know. And the independent is what they were changing. So they were changing the size of the particles. So they were making it small or large. This one, this is, who knows, but this is when you think of the exam. So when you start looking really in depth at the exams, and I'm going to get them printed and give them to you at some point. So outline in point form how we can investigate how concentration influences the rate of reaction. So in point form, so they just want dot points. So I'd suggest, okay, influences the rate of the chemical reaction. So I wouldn't just start afresh. It seems stupid when we've already given you this question. So I'd use the same one. I'd say I'd do exactly the same kind of thing, and I'd use the results maybe from this one as my control. Isolation has made me lose my ability to speak. I'd use this one, and then I would do different concentrations of this hydrochloric acid. So I'd just do different and do the same as I did here. So with this, don't overthink it. Maybe talk about how you would set it up, how you might make these dilutions, and very quick dot points. So don't overthink those questions and think you have to tell them everything. It's just when they say in point form, it's how you're going to investigate it. So if I say, how are we going to investigate this thing? I don't necessarily need a method. I need just a rough idea before we get into a bit more depth of that method. So this is one thing I think we need to work on. So this one. So, right, nitrogen and hydrogen gas, so NaCl value. So this is, again, is our Haber process. You're going to see a lot of questions around this when you're kind of doing questions, because it used to be on the study design. It's in the UK A-level, GCSE, maybe both. And, you know, it's a pretty common process. So, consider the concentration time graph. Concentration's here, time is here, which isn't labelled. But, you know, these things happen. Right, what happened in time one? So, remember, you're going to have these in, you know, you've got them in front of you in paper when you're actually going to be doing the exam. So you can scribble it over it. So I would do something like that. Maybe use a ruler if you have a ruler. So what happened at time one? So reached equilibrium. So that's what you can tell had happened by that point, more or less, if I wasn't so wonky. Right. So at time two, hydrogen gas was added to the system. Right, so we will go up like this, and then we have that scooping down, but not, where's your 2-pitch? Scooping down, but not coming down right down to where this was. So it's very small, so show it coming down. Indicate on the graph how the system responds. So this hydrogen has all of a sudden gone up, and then this has gone down. So we've added some of our hydrogen. So what's going to happen to our nitrogen is probably going to be the easiest to go from there. So we've got our nitrogen, and all of a sudden we've got more of this. So this is going to be more likely to react with it. So we kind of have a whoop. And it's going to follow. Is that right? It goes up. And then we've got a new higher position of equilibrium. Yep, no, that makes sense. Yep. Overthinking it. And then what happens with this is we're going to have, again, the same happening. That one's wrong. It goes up and then it goes down. It follows that one, doesn't it? It goes up and down. But it's still above. Right. They are going to give you bigger ones than this. You are going to use a grey lead, so it's not going to be like this big mess. But this one goes up sharply, then goes down. This one goes up more slowly because we've not had a sudden implant of it, but then it goes down. This one goes up and round because we're getting a different position of equilibrium because we've got more of this, so it's shifting this way. At time 3, the system reaches equilibrium, at which point a catalyst is added. How it would it respond? So whatever you've got here, it keeps going because the catalyst only lowers the EA and changes the rate. Oh, on the set of axis to the right, by the forward and change and mentioned. Oh, so this. Right, I'm going to think about this one on the right. How the rates of the forward reaction change as we do this. So let's try the first one, forward and reverse. I can't. My brain has gone fried.